Hi everyone, welcome to this lesson. So in this lesson, we are going to look at least squares approximation, and you're going to focus on the introductory part of or the introductory concept of least squares approximation. But before we start, let's look at this practical example. Let's imagine you have a set of data points on a graph. For example, marks of students compared with the number of hours they study. Now, if you plot those points on the graph, they won't form a perfect line. A perfect straight line. So they might be scattered here and there. So when you consider the graph here, okay, so they will scatter like this. Then the question is, how can you find a function like a straight line or a curve that goes close to those points and show the overall trend? And that's where the least squares approximation comes in. So the goal is to find the best fitting function, maybe a straight line, a curve, or an exponential function, by making the error as small as possible. Okay, so let's dive into our lesson. So in least squares approximation, the goal is to approximate a given data set using a standard function. For example, a straight line, a polynomial, or even an exponential function, as we explained in our example above. Now, suppose we have a set of data points xi, yi, where I goes from 1 to n. We want to find a function g of x that best fits this point. Now, at each point xi, the function value g of xi is only an approximate value. Sorry. So our g of xi here is our approximate value. Okay. Whilst the actual data value is yi. So the error at that point is ei, which is equal to yi minus g of xi. So let me explain this part. So we are saying that our g of xi here is our approximate value, okay, and our yi here is our exact data value, okay. So if you're having the exact data value and the approximate value, and you want to find the error, we subtract the approximate value from the what exact value. So e here represents our error. So our ei will be the exact data value minus what the approximate. Okay, so that's the error. Now let's consider the diagram below. So this is an approximation by a straight line, and on this graph, these points that we see here are our exact data points, and the straight line here is our approximation. So g of x is equal to a plus bx. Okay, it's our straight line and it's our approximation. Now we notice that the dots don't fall exactly on the straight line. Okay, these dots, you don't fall exactly on the straight line. Look at where they are and look at where the straight line is. Okay, so the vertical distance between the dots and the straight line is called the error, or it's known as the error. Okay, so we can see from the graph that we have u1, e2 up to ei. Okay, so when I is 1, you have x1, y1. When I is 2, you have x2, y2, and our error is e2 up to ei. Okay, so ei, where we have our point xi, yi. Okay, so we can see here that the error, that is the vertical distance here, is the exact data value minus the approximate data value. Okay, so our goal is to choose a line such that all these points or all these vertical gaps, okay, all these vertical gaps or errors are small as possible. Okay, and we can see that the vertical distance between this exact data value or data point and the straight line here is a little bit far. Okay, so you have to minimize the error. So our goal is to minimize the error. Okay, okay, so now the aim is to find g of x such that the overall errors across all these points is as small as possible, as we said earlier. But one thing you have to take note is we can't just add up all the errors. No, okay, because some errors are positive and others are negative, and they could cancel each other out, and that could give a false impression of a smaller total error. So let's also consider this practical example so that we understand the statement that we just made. So imagine you predict the temperature for 2 days. And suppose your predicted values are 22 degrees Celsius on Monday, but the actual temperature is 20 degrees Celsius. Okay, so here you predicted 22 degrees Celsius. Okay, but on Monday the actual temperature was or is 20 degrees Celsius. So in this case, we subtract the approximate value, okay, your predicted value from the actual the temperature, okay. So we are going to get 20 minus 22, which is giving us negative 2 degrees Celsius. And on Tuesday, we predicted 18 degrees Celsius, and the temperature is 20 degrees Celsius on Tuesday, the actual temperature. So here too, we get the error to be 2 degrees Celsius. Now, if we just want to add the total errors, then you're going to get E1 plus E2, which is negative 2 plus 2, giving you 0. So here, it looks like your total error is 0, suggesting a best fit, but in reality, you made mistake in both days. You get it? So the 0 here is telling us that, oh, your total error is 0, meaning you didn't make any mistake. But we saw that you made mistakes, okay? So we can't just add errors, okay? So in order to overcome this, one approach is to take the absolute errors, okay? So assuming we take the absolute errors of the mistake that you made above, the U1 and E2, then you're going to get absolute of negative 2 plus absolute of 2. Let me use the red one, okay? So this one is going to give us 2 plus 2, which is 4, okay? And this really makes sense, okay? But there's a problem here. The problem here is that the modulus, the absolute of EI here, is difficult to handle mathematically, especially when it comes to calculus like differentiation to minimize error. So instead, we use the sum of squared errors, okay? So we use the sum of squared errors. And here, we are going to square our error, okay? So we said that our EI is equal to, okay, so we said that our E is the summation of EI. Okay, I'll come back to this part. Okay, so if you are consider sum of squared errors, then you're going to sum the square of the what? The errors. Okay, so you're summing the squared of the errors. That's why we call the sum of squared errors. Do you get it? Okay, so we said that our EI is equal to yi minus g of xi. So when you do substitution, you're going to get this one. Okay, so in our practical example that we made about the temperature, if you bring that result you made here, taking the sum of squared errors, you're going to get -2 all squared plus 2 squared, right? Which is going to give us 4 plus 4, which is 8. Okay, so instead of taking the absolute values, we consider the sum of squared errors. Okay, and don't forget that our g of x here is a plus bx. Now our goal is to find the function g of x such that this total error e is least possible. Okay, that is why the method is called least squared method. So we want to find a function g of x said that the total error is as small as possible, as small as possible, as we said when we were. So let me come here. As we said when we were using the graph here. So we want to find g of x so that the vertical distance between the actual data point and the straight line is as small as possible. Okay. So in summary, the least squares method helps us to find a function that best fits a given set of data points by minimizing the total squared error. Hope you get it. Okay. So in our next video, we will go step by step to derive the constant a and b. So the constant a and b in g of x here. Please, if you found this helpful, don't forget to like the video and subscribe for more lessons. Thank you.